Yes, friends, in the previous lecture we have seen the multiple choice questions from our textbook of Physics Principles and Applications PHY 112 book by Nirali publication. We have seen 10 such multiple choice questions in earlier discussion. Today we are going to see chapter number 2, that is lasers and laser applications, and chapter number 3 is physics of molecules. Just like physics of atom, physics of molecule is also important part or important concepts we are going to understand one by one, as well as we will go for 7 to 8 questions on this particular chapter number 2, that is lasers and lasers applications. Now, what are the important things here? These are the different. What is the laser application? That means before application we should understand what are the principles of laser. Before that, what is the long form of laser? Light amplification by stimulated emission of radiation. Now there can be several questions on this simple word. Now, what do you mean by amplification? What do you mean by stimulated? What do you mean by emission? What do you mean by radiation? So all these 5 words can have at least one question. So in examination there may be a possibility that you will get some questions on the long form of laser itself. What is the meaning of each and every word, what it represents physically, how it is achieved physically, etc. These type of questions may be there. Apart from that, once we go for this principle of laser application, lasers, then there is one important phenomenon that is called as population inversion. This type of definitions may be important from the examination point of view. Apart from that, there are different types of lasers. Who invented laser? What are the types of lasers, etc. That type of simple questions may be asked. So ruby laser is one important laser. Then HENE, a gas laser, helium neon laser, that is one type of special laser. Then other than that, there are maybe other different types of lasers may be there, that may be asked. And important part of this is that apart from that, we can have several other types of applications. So what are the applications of laser? That important part is we should give much more concentration, that what are the different applications of laser, how laser is used in industry, what are the different applications of laser in medical physics, what are the applications of laser in the research field, then high speed photography. Then second application is in army or in defense sector. This laser plays a very vital role. There are several instruments and devices which work on the principle of lasers, right from weapons and from some survey devices, etc. And other than that, in environmental study, in the electrical and electronics engineering, as well as in printer technology. So many computer printers we are seeing today. These are called as laser printers. How these printers are being used. So there are many applications of these lasers. So this particular paragraph of applications of lasers, that we should give much more concentration, which is on page number 2.22 and 2.23. So my suggestion is that look at these pages. Chapter just a minute, pages 2.22 and 2.23 in our textbook. So look at these 2 pages, that there can be many questions may be asked on that particular applications of laser. So now let's come to the first question, of question number 11 in the series, that in helium neon laser the discharge tube is filled with the mixture of. So this is a gas at an pressure, a very low pressure. So that is around 1 mm of Hg. So what is this 1 mm of Hg means? Mercury. That is 1 mm of Hg. So this much pressure, which is in normal air pressure around us where we live, this is around 76 millimeters of Hg. That is mercury column height goes up to 76 millimeter in that particular device, and therefore the 1 atmospheric pressure is this. So we can remember or we can understand how much small a pressure this is, 1 millimeter of Hg. So we can go for this particular calculation. So 1 upon 76 atmosphere. This much small pressure is inside this helium neon laser tube, and therefore here there is a specific combination as shown here, 1 part of Ne and 10 part of He. That means if I have 100 grams of material or 100 grams of material or gas inside, out of that the 10 parts will be of this helium neon, and remaining 10 parts, sorry, 1 part will be neon and 10 parts will be this helium. So that much mixture is there. So mixture of helium and neon at this concentration, 1 part of neon and 10 part of helium is there. And why this particular simple combination? Other than that, the laser efficiency becomes maximum, or if this laser works with a maximum efficiency if this type of pressure is maintained and if this proportion is maintained. Other than that, if we go for 10 parts of Ne and 1 part of He, there is no guarantee every time that laser will be that effective or it will have that type of simple operations and so on. So this question number 11, first question, the discharge tube is filled with a mixture of 1 parts of Ne and 10 parts of helium, and the atmospheric or the pressure inside this particular gas, helium neon laser laser, this gas pressure is only 1 millimeter of Hg. So these two numbers are to be known, and then it is easy to answer all these questions related to that. Then question number 12, the lifetime of metastable state. Now you have seen earlier there are different types of energy states available. Suppose this is a ground state, and there is one more state that is called as excited state. Now we know according to quantum mechanics, in between states may not be possible sometimes. So depending upon the required condition, quantum conditions, the atom or the electron is raised from this location to this location. This is called as excitation, and when it comes back, this is called as de-excitation. And the time required in this case is in general, that means when this electron raised to the excited state and when comes back to this again ground state, that is called as a de-excitation. This time requirement is usually 10⁻⁹ seconds. So this is the normal excited state. Normal in the sense the electron does not remain for much more time, around 10⁻⁹ seconds. It is very small time as compared to 1 second, and therefore normally this electron gets raised and immediately it comes down in the time 10⁻⁹ seconds, and therefore these radiations are emitted there. So this is our normal phenomenon of the emission of radiation. On the other hand, in some elements there are certain energy states which are in between this ground state and excited state, which is called as metastable state. Now what is this metastable state? Metastable state is that this electron which is raised here comes down to this state, and in this case there is some small radiation is emitted which is very small of course as compared to this, but once this electron reaches at this location or at this stage, it stays there for some longer time, and this time is 10⁻⁶ seconds, that is 1 microsecond, to 10⁻⁻³ second, that is 1 millisecond. So sometimes there are certain energy states available in between excited state and ground state, wherein that excited electron may remain in a time period for 10⁻⁶ seconds to 10⁻³ seconds. So that means almost 1000 times more time this electron spends here, and during that period this particular state is called as metastable state. So in case of operation of these lasers, we are supposed to raise these electrons, large number of atoms, from this ground state to excited state. After some time, all these electrons do come in this metastable state. Almost all large number of atoms come in this state, and whenever there is a small radiation, the incident trigger is there, all these electrons which are raised in this metastable state, they immediately come down to this ground state, and this laser is emitted in this case. I think you might have learned all this operation in your classroom, but same operation is to be understood when we go for this type of states: metastable state, ground state, excited states, etc. And therefore lifetime of metastable state is this 10⁻⁶ seconds to 10⁻³ seconds. So this is what question number 12 option D is the correct option, that tells you the metastable state, the state which is different than this ordinary excited state or ordinary ground state. wherein this electron stays there for a longer time as compared to this the time required in the excited state, and therefore this time is 10 raised to minus 3 seconds to 10 raised to minus 6 seconds. So this is more, 10 raised to minus 3 is more than 10 raised to minus 6. This is microsecond, this is the microsecond, and this is the millisecond. So sometime this question may be asked, instead of seconds you are given second, millisecond and 1 microsecond. So sometimes this option may be given as 1 millisecond to 1 microsecond. So you should not get confused. 1 millisecond and 1 microsecond is just 10 raised to minus 3 seconds or 10 raised to minus 6 seconds. So this type of question may be modified, and you can be asked this type of question as given in question number 12. Now question number 13. Under normal conditions of or thermal equilibrium condition, this N2 is much greater than N1, N1 is greater than N2, N1 is equal to N2, and none of these. So this is what the number of electrons in a state. So this is, for example, these are the electrons in the ground state. I am calling this to be N1, and this is the metastable state, wherein I am calling this to be N2. Okay. And now this is the metastable state and this is the ground state. When these electrons are raised to some excited state and all these electrons come back to this metastable state, this situation, now count this number, who is bigger, N1 is greater than N2 or N2 is greater than N1. Depending upon that, we have different types of conditions. So in normal conditions, usually electrons in the N1 state is much more, and therefore the number of states which are having this N1 is large as compared to N2, and therefore this is called as normal condition. Normal condition is this. In abnormal condition, the number of electrons in the N2 state is much more as compared to number of electrons in the N1 state. That is called as abnormal condition, or that is what called as population inversion. So this word you might have heard earlier. This population inversion is related to this. That is what second question we are going to come across later on. So this N2 is greater than N1 is the state called as population inversion. Lot many number of atoms are raised to a metastable state. Therefore N2 appears to be more than N1, and that is called as population inversion. Whereas in normal conditions, this is not the condition. In normal conditions, most of the atoms are found in this N1 state, and very few number of atoms are found in this N2 state. Therefore option B is the correct option. Under normal conditions of thermal equilibrium or thermal equilibrium condition is that N1 is found to be much more than N2, and now there is no laser operation. So laser is not emitted, laser radiations are not emitted in this situation, and that is condition called as the normal condition. Whereas next question is question number 14. The population inversion is okay, this is thermal equilibrium condition, and this is the non-equilibrium condition, and that condition is called as population inversion. And herein that the number of atoms in the excited state, metastable state, is more than the number of atoms in the ground state. So whenever this type of situation is arrived or created by optical pumping operation, then we call this condition to be N2 greater than N1. So definitely there is going to be one question over this. Either this N1 is much greater than N2 or N2 is much greater than N1. This type of questions may be asked in examination depending upon this population inversion. So try to understand the concept of population inversion right from its basics, and what are its applications, how it is raised. So how this population inversion is achieved, what is the optical pumping, what are the different types of pumping, etc. These type of concepts and definitions must be known to you, as well as these conditions must be known to you. Mathematically, how to write these conditions, that is what this question number 13 and 14. So both these questions are important questions from the examination point of view. Now let's come to the question number 15. The active center in ruby laser. You might have seen the diagram of ruby laser. Ruby laser is it is called as semiconductor. So this is called as semiconductor laser. Semiconductor or solid state laser. Solid state laser. And from its operation, you might have seen earlier, we require a crystal of this Al2O3, okay, aluminum oxide, Al2O3 crystal. Okay, this crystal is, this is called as the what is called as the active center. So all the operation here, this operation of laser emission, that is possible in case of this Al2O3 or crystal, that is called as active center. And this active center, actually it has, I think you have drawn this diagram earlier. This is the major part of this active center, and there are two mirrors. So mirror one is semi-transparent, this is M2, and mirror M1, that is the completely reflecting mirror. And whenever this particular type of flash comes, because of this flash, the radiations are emitted here, and it goes forward and backward, and after getting a sufficient energy, these radiations comes out, and this is what your laser radiations. So this is the operation. So try to understand the complete operation of this type of ruby laser. So how these different types of levels are reached, how these different types of radiations are emitted, what are the components of this. Based upon that there may be some questions in the examination. So in case of ruby laser, active center is basically this Al2O3 crystal. Now depending on its size, depending on its length, etc., different types of different lasers of different capacity, that means its output, they can be designed, and therefore this solid state laser is another very important device or the component wherein we can create such type of lasers. Now these are very accurate lasers. These lasers are very popular these days as compared to helium neon laser and all that. Okay, so these are the only 5 questions which are asked in examination, which are asked in our textbook. Apart from that, as I said earlier, we have to go for different applications. I'll just go just revise in brief what are these applications one by one. So in medical applications, in medical there are several different types of applications of laser, and if you go for a list of this, medical applications are more important. So for different types of surgeries, okay, in spite of using this traditional knife, laser knives are used. So with the laser we can cut a very small part of the body. So for example, eye surgery. In eye surgery, this whatever problems in the retina or whatever mass that has been increased in the retina or other parts of the eye, this can be removed very nicely, very accurately, and in such a case these lasers beams work as a knife, and this type of several other applications may be there. So I'll just read it from the textbook. As the laser beam acts as a knife and its localized heating causes all the blood vessels to be sealed instantaneously, it is used to perform the bloodless surgery. So this is one of the very, very important application one must understand. So this is called as bloodless surgery. So here we are not needed to cut anything like our traditional surgery where there is a lot of blood goes out and that causes a lot many problem, but in spite of that, this laser surgery or this bloodless surgery is one of the very important application we must understand. And as I said earlier, in ophthalmology or in the operations of this human eye, this laser plays a very, very vital role and so many things. In brain surgery, CO2 gas laser or ND-YAG laser is properly used. Then argon and excimer lasers are used in angioplasty. So in human, that means in the operations, angioplasty operation of the human heart, that type of lasers are used. CO2 gas laser is used in the cancer surgery. So in cancer surgery also, CO2 gas has lot many applications, and lasers are used in dentistry for painless drilling and welding of the teeth. So remember these 5-6 applications of laser in medical applications. There must be 1 or 2 questions over this, and that's what we have to give a more concentration, as I said earlier, on the page number 2.22 and page number 2.23. All its applications of the lasers have been introduced or has been written. In military, in defense sector, what are the different types of devices and what are their applications. In high speed photography, what are the applications of that, that also we can go for. Then you might have seen in our computers we have this already now we are using this pen drives, but earlier we were using this CD drives. Now this operation, so whatever information written on that particular CD, this operation was to be read or to be operated by that particular CD drive. And what operation, the now application of laser is very nice there, nice application of laser, which is able to read this entire information and then further processing could be possible. So the CD drives which were being used in computers earlier days. This is what again containing a large number of applications. So, but from my point of view, you should concentrate more on the medical applications of the lasers, and that will be an important part of this chapter number 2, that is the helium, laser and laser applications. So, laser principles, two different types of lasers. Now, their functioning, their working, how these lasers do work. Then what is the concept of population inversion, and then what are the applications of lasers. So, these are the 4-5 points, as I said earlier, wherein we can concentrate over that. And also read this page number 2.27 too. So, page 2.27, this contains the summary of this chapter. Now, what is the summary? What do you mean by population? What do you mean by normal distribution? Then rate of absorption, stimulated emission, as I said earlier, light amplification by stimulated emission of radiation. So, every word carries a certain meaning, and its meaning can be found in this particular summary, as I said. Then there is a spontaneous emission, that doesn't require any trigger, whereas in laser operation we require certain trigger, and before that we need the stable state to be reached, that is called as population inversion. Already we have discussed this. Metastable state, active medium, lasing transition, these are the certain terms that are used in laser operations. Then pumping level, pump transitions, these are the some technical words. And what are the different types of applications of lasers. So, all these things can be studied very nicely once we go for this entire exercise. So, applications of lasers and the summary of this particular chapter, that can give you that can give you a confidence, and you can solve very easily all the numerical as well as all the small MCQ questions asked over this chapter number 2, that is laser and laser applications. Okay, now let's move to the next, that is the question number 16 onwards. These are the questions of the physics of molecules. In the first chapter we have seen certain questions on the physics of atoms. Now physics of molecules. In this case also we have to understand, that means I think you have studied earlier these different types of bonding exist. So, how chemical compounds are formed because of different types of bonds. So, depending upon chemical compound, different types of bonds are exist. So, ionic bonding, covalent bonding, metallic bonding, and other than that there is van der Waals bonds too, but that is in case of the liquids. But here in case of materials, solid materials, almost these 3 different types of bonding situations are there, or bonding conditions are there, 3 different types of bonds are there. So, you have to understand very easily what these bonds are, how these bonds work, how transitions of electron takes place from one atom to another atom, and based upon that this type of materials are created or compounds are created. So, very simple question number 16, sodium chloride NaCl is formed by, and for that we must, before that we go for this particular type of compounds, we must understand the electronic configuration of each element. Sodium is containing 11 number of electrons, whereas Cl has some different number of electrons. Now, how one of the electron in the last orbit of the sodium, that is shared or that is given to the chlorine, it becomes a negatively charged ion, whereas sodium becomes a positively charged ion, and such an ionic bond is formed in between these two elements, and that forms one molecule of NaCl. And once this molecule is formed, then crystal of NaCl is formed, which is a simple cubic crystal, and therefore ionic bond is the solution of this question number 16. That is the correct answer. So, sodium chloride is an ionic compound, and therefore ionic bonds are formed there, whereas covalent bond and metallic bonds, this is the different things, which is not correct answer here. Now, question number 17. In the molecule H2, hydrogen molecule, the hydrogen atoms sharing electrons via covalent bonding. So, here if I go in this case, earlier case, this H2 is, this is one hydrogen atom and this is another hydrogen atom, and this electron here, this electron is shared to this, and this electron is also shared to this. So, every time in an orbit for an instant, there are 2 electrons are found here. After some time, both of these 2 electrons will be observed here, and thereby these 2 atoms remain in the bound state for a long time, and that is what called as, this type of bonding is called as covalent bonding. Both of these electrons are shared equally by both of these two atoms, and therefore H2 bond is formed, and therefore the number of electrons required there to have a stability of this orbit, first orbit, that is 2, and therefore 2 is the correct answer of this question number 17. So in the molecule H2, the hydrogen atom sharing 2 electrons via covalent bonding, therefore such type of covalent bond gets formed, and there is a stability to this molecule of hydrogen or H2 molecule, and that is very nice case of this covalent bonding. So all these things you might have studied earlier in case of this particular chemistry, all these things. Now dissociation energy of the hydrogen molecule is, now what is this dissociation? Once this H2 molecule is formed, okay, like this is the H2 molecule, so electron is shared. Now to separate out this, how much amount of energy is required? So one separate hydrogen atom and another separate hydrogen atom, this is called as process of dissociation. So here you have to remember this number, the amount of energy required to dissociate this H2 molecule, this is exactly 4.52 electron volts. So here no need to go for calculations and anything, you should directly remember that dissociation energy of hydrogen molecule is 4.52 electron volts. Now note that this won't be same for all other type of covalent molecules. So another type of covalent molecules, depending upon number of electrons, how many number of electrons are shared, what is the nucleus size, what is the atomic size, based upon that this energy may go on decreasing or increasing. For different type of covalent molecules, different dissociation energy is possible, and here in our case, this dissociation energy of hydrogen molecule is found to be 4.52 electron volts. Now you can provide this energy externally either by radiation or by heating or some other method, and thereby we can separate out two different atoms of the hydrogen from each other from this molecule, and this process is called as dissociation of the hydrogen molecule. Question number 19. The methane molecule of the carbon atoms form. In methane molecule, the carbon atoms form dash number of covalent bonds with the hydrogen atom. So you might have know this is CH4. The chemical symbol for this methane is CH4. So there is one carbon atom at the center, and there are 4 hydrogen atoms are connected from to it outside. Okay. Now there are 4 electrons there, and there are 4 electrons here in this hydrogen. Now all these electrons, when these electrons are shared in the last orbit, then this becomes an 8 electrons in the last orbit, 4 by hydrogen and 4 by this carbon, and therefore this covalent bonding forms there, strong bonds are formed there, and the formation of CH4 is possible. So all 4 hydrogens share 1 electron to this orbit, whereas this carbon atom share 4 electron to this orbit, and therefore stability of the orbit is possible, and 8 number of electrons are shared by all these, and therefore this type of bonding is called as covalent bonding, where this 4 is the correct number, which tells you that this many number of hydrogen atoms share their electrons each to this orbit, and therefore the stability to the compound is possible, and that is the compound that is called as CH4 chemically, or its traditional name is methane, as we have seen in this question number 19. Then when temperature increases, electrical conductivity of covalent germanium and silicon crystals. So silicon and germanium, these are again in from the same group where the carbon atom is. So both of they have also 4 number of electrons in the available in the last orbit. Now these electrons can be shared with other elements as well as other different same atoms, another atoms, and therefore possibility of sharing all such 4 electron is possible, and therefore the crystals of germanium and this silicon, they are basically covalent type of crystals, and therefore as we know, the number of electrons available for conductivity once at very low temperature or at normal temperature, number of free electrons available for conduction is very less, and therefore conductivity is very small. But when we increase the temperature of that crystal or that sample, then some bonds are broken and more number of free electrons are made available for conduction, and therefore its conductivity goes on increasing. Therefore at very low temperature or at very small temperatures, almost the conductivity of this type of germanium as well as silicon crystal is almost zero. They are insulators. So based upon that, we can go for this type of 3 definitions. Insulators, that means they do not carry current at all. Then second is the semiconductor, and third is the conductors. So as we know, in case of conductor, large number of free electrons available for conduction, whereas here no free electrons available. And here moderate or intermediate, some intermediate number of free electrons are available, and this is possible. That means, as I said, at very low temperatures both of these materials are as good as insulators, but when some temperature is increased, now these insulators becomes the semiconductors, but they will never become a conductor as like metal. So all metals like copper, iron, etc., where large number of free electrons are available, and the bonds formed in this type of materials is metallic bonds, where these particular electrons are found to be that with free electron C. Okay, and in that particular, these atoms are of that particular material there, and therefore large number of electrons are available for conduction. These are called as conductors, and semiconductors are the material where a moderate number of or intermediate number of free electrons are made available after hitting the insulator or this breaking the covalent bonding. Some of the electrons are made available, and therefore this as temperature increases, conductivity of this material goes on increasing. Whereas in metal, you might have heard earlier, in case of metal, when we increase the temperature, its conductivity decreases. So in case of metal, conductivity decreases as we increase the temperature, whereas in case of semiconductors, this conductivity goes on increasing as we increase the temperature, or when we add some material, that is called as doping. By adding some other type of material, that process is called as doping. Again, the number of electrons or number of holes, positive holes, that we have can be made available, and therefore we go for that type of materials which are called as semiconductor materials. But here in this question number 20, we have to remember that this answer of question number 20 is A, that the temperature increases, the electrical conductivity of covalent germanium and silicon crystal increases. Now question number 21, two atoms will make non-polar covalent bond such as HH when their electronegativity is now non-polar. Non-polar means they are in the same line. This is, whereas in some cases we get this type of bond, this type of materials form. So this is, for example, oxygen, and this is hydrogen, and this is hydrogen, like H2O. Now this is a polar molecule. Here positive charge and negative charge center of molecules are at different location, whereas in some cases this positive and negative charge centers are at the same point, and this is called as a non-polar molecule, whereas this is called as the polar molecule. So non-polar and polar, therefore two atoms which will make non-polar covalent bonds such as HH when their electronegativity is equal. If this is unequal, then it becomes polar. If it is equal, then it becomes a non-polar. So that is from the chemistry also, we might have seen this earlier, that the formation of bonds and the polarity of that particular molecule, that has a very clear-cut relation, which is shown by these two examples. In case of H2O, we have a polar molecules, whereas in case of non-polar molecule, we can see there are several examples like HH or hydrogen atom, hydrogen molecule. Now question number 22, a covalent bond formed by mutual sharing of one electron pair between two atoms is, this is called as a mutual sharing of one electron. It's very simple question, simple answer is there, single covalent bond. If we are sharing two electrons, then it is a double covalent bond, triple covalent bond, as the number of electrons goes on increasing. So here when we are sharing one electron pair of two atoms, then it is called as a single covalent bond. So question number 22, correct answer is this, that is the single covalent bond. Now this is one more very typical question, question number 23. This is the last question from this chapter number 3, that is the molecules, physics of the molecules. So if R is the separation between two molecules, the dipole-dipole interaction energy between two molecules is proportional to. Here this is the last article of this particular chapter, where we might have seen how this type of elements or how this type of materials are how to go for this calculation of this energy. You might have seen let me come to this particular thing. So there is one relation which is called as total potential energy of this particular type of bond, which is given by V is equal to V attraction, this potential, and plus V repulsion. Repulsion. And in both the cases, when we actually see all these numbers, this is found to be R alpha upon R raised to m, and plus this is negative since it's an attraction, and it's a repulsion, therefore it is positive, so beta upon R raised to n. Now we have to go for this condition. For that case, there is one simple problem has been asked. So this particular force is given by gradient of this delta V upon delta R, that gives you the force. And if there is one numerical example, and in the book we can go for solving all this example. This is given in your textbook on page number, please see, on the page number 3.27. So page 3.27, sorry, 3.27. On this page number, this particular example has been solved there, and that example shows you, if I go for derivation of this delta V upon delta R at certain value of R is equal to R0, I get a very simple calculation, and that calculation shows you this R0, okay, raised to 13 upon this R0 raised to 7. Okay, see this example, numerical example. This comes to be 12 upon 12 beta upon 6 alpha. Okay, so this constant alpha and beta, and this particular proportionality, if I go for this calculation, 13 upon 7, that comes to be R raised to 6, R0 raised to 6. So this distance raised to 6, that's why R raised to 6, R0 raised to R raised to 6 dependence is there. Therefore, in the separation between the two molecules, the dipole-dipole interaction of energy, so we get the minimum energy here. So to make it to be 0, we get this condition, and from that condition I get this R0 raised to 6 is the condition, and therefore this C R1 upon R raised to 6 is this the separation required here. So if R is the separation between two molecules, the dipole-dipole interaction energy between two molecules is proportional to 1 upon R raised to 6. And that is what this particular example is, a numerical example, big example, doesn't matter, just remember, in such a case, to have the interaction energy of this molecule to be a minimum one, we require this condition to be that distance between these two atoms, between these two molecules, should be R0 raised to 6, or in proportionality constant we can be 1 upon R0 raised to 6. So 1 upon R0 raised to 6 is the dependence that can be understood here in this case of a dipole-dipole interaction between two molecules. So these are the few questions from this chapter, as I said. Now in this chapter, so what are the important definition we need? As I said earlier, what is the ionic bond? So you have to study the definition of ionic bond. So what ionic bond is, this is one important definition. Second is also we have to go for study of this covalent bond. What do you mean by covalent bond? How it is formed, what are its properties, characteristics, etc. That is required. Then what do you mean by covalency? Now different elements have covalency, different one. For carbon we say its covalency is 4. How these particular numbers are there. Then how hydrogen bonds. Hydrogen bonding is, as I said earlier, this is one special case where we can go for study of this hydrogen bonding. So how these hydrogen bonds are formed, we require some understanding of this. Then metallic bond. This particular metallic bonds are altogether different than this covalent bonding as well as the ionic bonding, and still today people are not able to understand the exact nature of metallic bonding. So whatever information we do have about this bonding, that information is almost not at perfect. So this metallic bonding is one of the strongest bonding that bonds all the atoms of the metals together, and therefore different types of elastic and metal properties are possible, and this metallic bonding is this. So these are the few important topics and the concepts that are to be understood from this chapter number 3, that is the physics of the molecules. Here we can go for, again as I said, go for its summary on page number 3.28. You can get all these informations in a very short and simple words, and that can be applicable to solve the MCQs which will be asked on this particular chapter, on this chapter number 3. So here today we have discussed chapter 2 and chapter 3 MCQs that have been asked in textbook. Apart from that, other type of simple MCQs may be designed for these chapters, and all its answers can be found in the summaries of chapter 2 and chapter 3. So my request for you all, just go for summary of this chapter 2 and chapter 3, and you will get lot many concept will be understood, and based upon that you can able to solve the number of numerical as well as MCQ questions on this chapter 2 and chapter 3. So here we have finished this particular chapter 1, chapter 2 and chapter 3. In the next lecture we will go for this last two chapters, that is the sources of electromagnetic waves and applications of electromagnetic waves. So these two chapters will be covered in the next week. So thank you for